Okay. Welcome back, everyone, for the last day of the school. I hope you have had a good time so far. We have been learning quite a bit of theory over the last few days. So a natural question, if you especially come from the data side, is, please show me some data. It's been was all elegant, beautiful mathematics. Well, great. But what does it mean in real world? Is there really any data that demonstrates that tipping points exist in real world? And secondly, do any of the metrics like early warning signals, are they they may all be good in theory, but can they actually be measured in practice? So this is something we haven't really touched upon so far. I thought maybe this could be something we can discuss today. Okay, so one of the examples often cited as an example of catastrophic shift in ecosystems is that of desertification. The map there shows a familiar picture, Northern Africa, which we know as Sahara today, right? And this massive landscape, massive desert landscape, some thousands of years ago, wasn't like this. So apparently, it was actually full of vegetation, many megafauna, that then, according to this proxy data, so this is a proxy data of vegetation that, as a function of time. And typically, you obtain these vegetation proxy data using various sediment compositions. And in this case, the lower sediment of this specific sediment means that there was high vegetation, and the higher one means large. And as you can see, the switch between these two happened rather rapidly. Of course, remember the time scale on the x-axis. We are really looking at thousands of years here. So compared to the fact that this this landscape was stable with some ecosystem type for thousands of years, it switched to another type over a relatively small window. Of course, if you now zoom into that window and if you get more data, it may look gradual, but the idea is, compared to the time scale over which they were stable, the transition appears rather abrupt. And in fact, the more recent understanding of this system is that there were many such local events which were probably rapid. Of course, if you now look at the entire landscape, it will appear a bit more gradual. And of course, always remember one thing, right? Whenever we see an abrupt transition, it doesn't necessarily mean it's a tipping point. What's an alternative hypothesis? Huh? Sorry, please say aloud. Yeah. So one is stochastic transition across the unstable branch. Let me argue it may not be even that. Maybe there are no two stable states. So that would be still consistent with two stable states, right? Is it still possible that there are no two stable states here? Yeah. Okay, oscillatory, yeah, another possibility, yes. What else? Okay. Okay. See, remember that one of the defining features of tipping points was that there's a large response for a small environmental change. Now, how do we know the latter is true here? How do we know the environmental changes itself are actually minor? That's not very obvious, right? That's not guaranteed. Just because I see it doesn't mean the driver itself changed, change only by a small amount. It's possible the driver itself also underwent a transition like this. Therefore, this went a transition. Now, for these type of large scale ecosystems, people usually argue that the drivers are of, are also global drivers. And in fact, for this kind of large scale ecosystem shifts and climatic shifts, one of the reasons that is attributed is the slow precession of Earth around its axis. Okay, and for example, even you are probably familiar with the Ice Age related climatic shifts as well, right? So those are all often related to the small changes in the precision. But as we know, those are actually gradual changes. Earth is not suddenly doing anything like this. It is just, in fact, so basically the incoming solar radiation strength changes as a consequence of small precession around the axis of rotation of Earth. And it is hypothesized that those solar radiation changes, which are actually gradual, that led to a gradual change in energy flux, but that in turn led to a whole series of feedbacks in the climatic systems, including the monsoons, that leads to these vegetation shifts. Okay, so to argue that the environment was gradually changing is a subtle, very difficult and subtle exercise. And this is one of the papers that argued this. I know this was probably a large scale climatic shift driven by a small change in the driver. And this is an example of an opposite extreme. We were looking at really large scale, right? Really continental scale. So here I'm showing you a much smaller, like few hundred meters by few hundred meters out of a area, maybe a few kilometers square area. This is a grassland area. What you are seeing here is again, still large enough from what we are used to, but it is still about a 60-year long time scale. What you are seeing here is that in the initial window, you see that the grass cover was relatively low, hanging around 10%, but eventually it settles down to around 40 to 50% grass cover, and it stays there. Okay, so now if you see a time series graph like this, is this again an abrupt transition? Is this a, for example, R tipping? Is it B tipping, or is it a stochastic transition? So we have learned about three types of transition, right? One is a transition that happens at the tipping point. We could also call the critical transitions, right? And then we have an R tipping, which you learned yesterday, and then we also have you are away from the tipping point, but the stochasticity drives across to an alternative stable state. Those are three possibilities. All of them work broadly under the assumption of some an alternative stable states theory. It's also possible, as we discussed in the last example, that environment itself changed a lot. Okay, now given the data like this, even on a relatively proximate, smaller time scale, to sort of arrive at which of them actually happened is a non-trivial exercise. Okay, so in fact, I will discuss this data set a bit, in detail in the later slides. But this is actually an example of, by the way, grassland recovery. The low grass cover actually, shifts to a relatively large amount of grass cover. So basically, a pretty barren state gets converted to a grassland state. Okay, and one of the classic examples in ecology that actually led to a spurt of this entire field actually comes from lakes, studies on shallow lakes. Steve Carpenter and Martin Scheffer, these are the two people, lake ecologists. They were trained as limnologists and lake ecologists, and they were two groups, one in Netherlands, other one in US, who sort of studied the possibility of alternative stable states using data as well as models in many lake ecosystems. And here, of course, data are really sparse. Here, there is some evidence of hysteresis-like phenomena, meaning, when the total phosphorus in the lake increased, and some measure of the lake quality undergoes a dip. Those red lines are the ones when the forward transition happened. from a good lake to a sort of, these are all, subjective words that I am using, a good water quality lake to a bad water quality lake. But when the driver was reduced, it doesn't trace the same path, but these black dot data points, they show the recovery path, and they're distinctly different from the one that went forward way. Okay. And then, another example, if you read these papers that talk about critical transitions, catastrophic shifts, financial meltdowns are often cited as an example of catastrophic shifts. One can again ask, oh, is it truly the case? How do we even say something is a tipping point, critical transition? The same questions that we have been asking applies. So one is, show me data is one thing, but then, okay, I showed you data, but how do I make sense out of this data is also a very challenging question. Okay, so remember that at least theoretically, the characteristics of these transitions are that you have abrupt changes in the state of complex systems. They typically happen for gradual changes in the driver, and sometimes these could even be irreversible. And of course, this irreversibility is debatable. It depends on the kind of system you're talking about and time scale you're interested in. For example, species extinctions are irreversible, but ecosystem changes might still be reversible. Okay, and of course, we have used a whole bunch of terminology. I haven't added R-tipping here. One of the terms that is actually used is also called regime shift, and that word regime shift actually comes from social sciences. You are actually trying to change the political regime, and one of the early hypotheses also, they are also like tipping events. When certain mass movements happen, it leads to changes in the regimes, and those mass movements sort of get triggered. And as you can see, there are always rebellions against the regime, right? But some of them, most of them die off. But some of them, through a series of positive feedback, actually ends up changing the regime. Okay, and abrupt transitions, tipping points, critical transitions, stochastic transitions, bifurcation points, hysteresis. We have heard all these terms. I should add R tipping, B tipping, and N tipping, the other types of classifications in tipping point events. And then one question, as an applied perspective, from an applied perspective that we were all interested was, one is, okay, are these even tipping points? That's one question, right? The second question is, or what kind of transitions they are. Second question is, how do we mathematically model? We have spent a lot of time doing that this week. If you now had only data preceding to each of these, what looks like abrupt transitions, are there, could we have, detected an impending catastrophic shift? Okay. So, and that's the question of, great applied importance, and, the idea of systems slowing down near critical points, the potential changing in its characteristics, and that in turn leading to various potentially measurable changes is the basic idea. We can ask, how much are these mathematical ideas true? Okay, I can model all these systems beautifully using equations. One way to test a model is not just how well it potentially explains what we have observed, but also can it make predictions that are sort of non-obvious, and can we sort of, look at those predictions in the real data. Okay, so I thought we will just discuss some of these things today. And just a quick recap, this is the model that Partha presented. This model has many features of the various data sets we have just discussed. It has a simple logistic growth, and it has this loss due to grazing or predation. And what is interesting about this model is that there is this intermediate region where two stable states can coexist. Okay, so we have done enough of this, so I won't really say much more. And basic idea of all the sort of, both the how stable states coexist and the early warning comes from this idea of potentials, right? I know if you drop a ball, it comes and settles down here. If you drop it here, it comes here. So that explains the idea of hysteresis. And as you're approaching tipping points, the shallowness of this landscape, changes, and that leads to many types of fluctuations. And by characterizing fluctuations, we can potentially suggest early warning signals. So that's a basic idea. Okay, so one term that we haven't really discussed well enough is something called resilience. That's very frequently used in ecology, and this word resilience was coined by Holling in 70s. The way he described resilience was, if this is the current state of the system, what is the maximum perturbation it can absorb without undergoing a massive change? So, for example, in this conceptual landscape, the maximum perturbation it can absorb is up to this point. Okay. So the resilience of this ecosystem will be whatever this strength of perturbation is. On the other hand, here, a ball here will also have resilience given by the width from the current stable state to the edge of the valley. So that's called the resilience. Now, this is also called ecological resilience. Now, one of the criticisms of this resilience was that, hey, look, how will I ever measure this? If I do actually end up doing a perturbation like this, it's going to be catastrophic for the system. We don't want to be even doing such experiments. So how can we even measure this? Is it a really measurable, useful quantity at all? And then that led to the idea of what engineers called engineering resilience. And engineers defined resilience as return rate of systems from perturbations. And that is like, I won't make a full perturbation, I just make a local perturbation here and see how fast it recovered. And then, as we know from the theory we have learned so far, and that return rate becomes smaller and smaller. Is it right? Recovery times becomes larger, so return rate becomes smaller. Okay, as we are approaching the tipping point. So in fact, now even ecologists have moved to what previously was called engineering resilience, and because that's a more measurable quantity, and you don't have to do massive perturbations to figure out. Okay, and again, I'll skip this entirely because this is good enough. Okay, so just to give this is the same graph that Partha also showed. This is a simulation of a model where the resource biomass undergoes a transition, and then and you're slowly increasing some environmental stressor, because of which the resource biomass underwent a transition. And then what you find is that autocorrelation increases, standard deviation increases even before the transition has happened, and the skewness decreases. Basically, it's all properties of fluctuations. They all show characteristic patterns, and therefore, if we can measure these patterns, maybe we will know that this crash is imminent. That's the basic idea. And let's see if this is really true. And how do we go about actually knowing if I am at the tipping point? If I really can measure these things, that's the basic question. So now, where does empirical evidence come from? This, much of these theories were developed in between 2005 and 10, and then one can, people began asking these questions both in laboratory systems and in field systems in the context of ecology. So, for example, in the laboratory system, we can ask, if you push a system to a tipping point, if you slowly drive the system to a tipping point, do you actually find these early warning signals? Again, now this is a much harder question to ask in the field. First of all, how will I even drive a system to tipping point, right? It's very hard, and we have much less control about real ecosystems. But what one can do is, if we know of ecosystems that have gone past a tipping point in the past, and if we have data, we can take those and do measurements. It's a post facto analysis, but something is better than nothing, right? So these were the two approaches that people took. In laboratory system, you actually actively drive systems to a tipping point, and in the field systems, you actually check previous data sets where there is evidence of tipping points, and see if it works. Okay, let's see. So one of the first paper that did this was a paper by John Drake, who was actually supposed to come next week, but he later on could not come. Okay, so early warning signals of extinction in deteriorating environments. So what these people did was basically cultured colonies of Daphnia in laboratory in laboratory conditions. Daphnia is one of the really tiny swimming organisms in lakes, and so the ecosystem that they had was basically these populations of Daphnia in small dishes in the laboratory system. So and of course they did this under controlled conditions, as well as conditions where the certain environmental conditions were getting worse day by day. And they ran these two experiments, controlled lines and the deteriorating lines, over a period of 1 year. Okay, and then they studied 4 early warning signals: variance, skewness, correlations in time and space, and then they estimated that from another set of experiments, they estimated that this system has a tipping point. And they were reaching conditions of tipping point by 300th day in their experiments. And then here you see the data. Oh, okay. I'm sorry, I forgot to put the data of the crashing population itself. Actually, it turns out that in this population, you don't see a very evident crash per se. It's actually a continuous transition. So, it's not really an abrupt transition of the type we have discussed so far. Is actually a continuous transition in the system. But as we know, the theory of critical slowing down and all the fluctuations actually hold true exactly as nicely for the continuous transition. Right? So what they, as I said, this, so this is measure of variation. This is skewness, 2 fluctuating measures of fluctuations. And this line here is when they estimate that the drivers have reached tipping point. Okay. And the black line here represents the control conditions, and the blue represents what happens in this. So what do you observe? Do you think it's a reasonable data that convinces that some of the predicted measures are increasing even before reaching the estimated tipping point? Is it reasonable? Okay, of course, it's a very controlled experiment, under controlled conditions, this is happening, this increase, if you have to ask a critical question, when could I really detect statistically the difference between these two lines? That could be maybe a few tens of days before the actual tipping point. Okay, but nevertheless, at least in principle, the predictions seem to work. Is that fine? Okay, so this was this was actually, to the best of my knowledge, of the first study that looked at data. Actually, technically, it's not fully right. The entire, you'll be really surprised to know, despite the fact that a lot of the work happened in the last 2 decades. Actually, the first paper that tried to think of this entire system from a predictive point of view was a paper by Wiesel in 1984. In your Ecologia. Okay, we should not forget to acknowledge that book, that paper. Okay, that paper proposes that the characteristic time scale actually goes to 0 when we approach bifurcation points. It basically borrowed ideas from physics and then applied to dynamical systems and showed that the return rate actually goes to 0 at bifurcation points. And they also do experiments, if I'm right, in that paper. I don't know how maybe the standard the new methods of statistical analysis, I don't know how well they apply there, but at least that paper claims that they also had empirical evidence for the same. So in some sense, the entire idea was actually done by somebody in 1984, but I don't know if anybody else followed up on that idea in the following years. And sometimes it also tells something about the way science works. And then there were these 2 papers in ecology in 2006 and 7 by Steve Carpenter and Martin Scheffer. Okay. And these two are leading scientists working in the field of lake ecosystems, and they proposed variance and this critical slowing down, the same idea that was there in 1984 paper, okay, as a measure, okay, but in more complex ecological models, okay. And then that then led to a large number of studies trying to do the same, okay. So sometimes unless a critical, I mean, it's a sociological aspect of science, right? Sometimes unless a critical mass of scientists simultaneously work on something, even if it's very important, others may not follow. Okay, so nevertheless, coming back to this, so I should correct myself that this was not necessarily the first experimental study. There was this study in 1984 that did both the theory and experiments. Okay, and they found that among the 4 indicators, the effect was most prominent in coefficient of variation at space. So this was one experimental study, but the drawback here was this, as I mentioned, this was actually not a tipping point the way we have been defining, where if it's a critical bifurcation point of the saddle node bifurcation that leads to an abrupt transition. Technically, it was not really that. Yeah. Yeah, you can't. So that's an open question for you to answer. When will the transition actually happen? That cannot be answered from these indicators. But that is not valid in the model. So you should distinguish between driver crossing the transition state and the response variable transitioning. Okay, there is always a lag. Okay, so now few more empirical studies that followed. So this was in 2012 or so by a physicist in MIT who studied yeast populations. So now look at the X and Y axis. Y axis is population density, and X axis is an environmental factor. More like basically how much food you are giving to the yeast populations. What do you see here? You see, and there is a branch here, a stable fixed point branch, and there is an unstable fixed point branch, and then there is a extinction branch, almost exactly like what we had in that harvesting model, right? So, and in that sense, this experimental study was truly now getting to baseline conditions in a system that was reflective of what happens in a mathematical model. So if I had removed these data points, if I had shown only blue and red lines, you would have been convinced this is just a result of a bifurcation diagram of a mathematical model, right? So yeah. How do you get the unstable points? You answer the question? No, you can. I'm sure you can think about it. How would you estimate this line? You just start, huh? Yeah. So you just start various experiments, take this dilution factor, start experiments across various initial conditions here and see where all do they go. There will be many of them will come down, many of them will go up, and know where it is. That's a line separating the two. Of course, it won't be a line, it will be more of a cloud of small cloud there, a band there. Yeah. Yeah, absolutely. Great question. So there are many methods to do that. If you have generated time series from your experiments, right? You can look at the first thing I would always do is to plot the histogram of the data. Okay, if there are now only one mode in your histogram. Okay, the first question is it even in a steady state? Now there are many methods of testing stationarity in time series data. Okay, right? in the, and that's one way to do. First is test for stationarity, which basically means that, are there some properties of time series that do not change with time anymore, right? That's one thing to check. And second thing is, if you are now convinced it is stationary, look at the histogram of the data, probability distribution function, estimate the distribution function, and then look. If it now has two distinct modes, that's evidence that there are two steady states. Okay. Yeah, so there are no easy answers to this question, right? I mean, if you started off really far away from your steady state, it would take a long time to reach there, right? But if you had started your experiments close enough, you would have reached steady states quickly enough. Okay, now, it's also possible that when you look at steady state, you may find a single mode because it never underwent a transition to alternative stable state. So you will conclude that the system has only one. Okay, so therefore, people do experimental manipulation. So here, what they're doing is they're doing experiments with many different conditions for a given dilution factor. And some of them go extinct, some of them actually go to a large population density, right? So controlled experiments, therefore, are very important. If you only rely on observational data, for example, in the grassland data I showed you, in the first 30 years, we would have just thought there is a single stable state of 10% grass cover. But only because there was a long enough time and it underwent a transition, we now know there are two states, right? Or maybe if you wait long enough, there will be a third state. We don't know, right? But experiments allow you for a better control over the outcomes and what's the underlying. And of course, and of course, you read this paper in Science actually by I think Dye et al. 2012. Where they also provide a mechanism of positive feedback in the yeast populations that maintains these two one extinction, one high population density, but exactly for the same driver value. And then what they did was once they've established this, they actually subjected population, a set of populations to increased dilution factor, after which system underwent a collapse. And then they measure, again, the same metrics. They find that variance, standard deviation, autocorrelation in time work well, but not the skewness. Okay, so these three metrics worked well in their populations, but not the skewness. That was the finding of their study. And this again, a laboratory, highly controlled study. And following this, there were a few other studies. One where there was an experimentally induced regime shift in the aquatic food web. You can imagine how difficult this experiment must have been. Where actually, again, one thing that I find it striking, if you read this paper, you will find that they find that variance and skewness work better than the autocorrelation. And something consistently I have found across studies is that whenever fluctuations are dominant, autocorrelation as an indicator doesn't work as well, but the fluctuation-based measures like even standard deviation, skewness, even kurtosis actually works better. Okay, and it sort of makes sense. When there are more fluctuations, the ball in the landscape explores, larger, width, and therefore you will actually experience the moments, compute the moments better as well. And then another microcosm experiment, and there was also a study. Now coming back to field data, right? What you can do with field data is, analyze past data. And this paper analyzed a whole bunch of climatic shifts in the past, and it computed only the autocorrelation, not other indicators. It found that across many of them, the autocorrelation of time, of the autocorrelation in time of the state variable is a good indicator. Okay. Now this was, there are now over the last another 5 years also, there have been more experimental studies, including even in engineering systems like the Sujit's group, right? So I'm focusing mostly on the biological side here. But that said, yeah, go ahead. So can you explain? Can you sort of rephrase the question again? What do you mean by half the time it doesn't work? Like, you measured 100 time series, it didn't work in half the time. Yeah. Okay. What do others think? So the idea is that, now you have to understand the theory a bit better to combine. So to be very clear, um, variance and autocorrelation, if you look at the formula that Partha wrote, they're basically almost identical formulas, meaning the coefficients that go into them, if they have the same value, they will have basically similar values. Okay. Now, but with a small subtle difference, which is that if the external forcing is large, variance will increase, but not autocorrelation. Okay. So variance has two terms. If I can just write this. If you look at the time series variance of some state variable, it's proportional to the external variance by alpha, where alpha is the return rate, or the what he was writing as alpha is basically modulus of gamma. Okay. So this is how the variance in time series goes. Because alpha goes to 0, you expect the variance to blow up. Now, if you look at the autocorrelation in time, that goes as, can you just remind me, it's 1 minus something, 1 minus e power minus alpha, no? Something of the order, I would have missed some, yeah. Yeah. So basically now in this equation, there's only alpha but not sigma e. Okay. So when alpha goes to 0, this term goes to 0, therefore the autocorrelation goes to 1. Okay. Now you can see that in both of them, alpha is the one that is driving if you are going towards a tipping point. Okay. But the distinguishing factor is this, the external noise. Okay. So which means that if it has some information that this doesn't have. Again, if you look at the skewness, okay, that is driven by a not just sigma e square, it also depends on some interaction with beta. What is beta? Beta is the nonlinear term which was not part of the stability analysis at all. So it depends on a nonlinear term. So but now there's a fourth metric which is not mentioned anywhere here, which is called spectral function. Okay, that is basically Fourier transform of this. Now, if you take some function, do a Fourier transform, you're not going to get any new information out of this. It's going to be the same thing, right? So basically, you can see that there is some, you can actually combine these three because they all add different information potentially. Okay. So therefore you can combine them. Imagine, but if they were all driven by the same process, then I can't combine all of them. So I think given that if you see that all of them are increasing, that means that it's a strong indicator. If only a few of them are indicating, are changing, then it's a less stronger signal. I think one can arrive at those conclusions. Okay. Yeah. Okay. So now, so these were various experiments, but but still, remember that this was not an experimental work, but these two, this one as well as the one I showed you previously with Daphne, they're all experimental work, right? So doing this in the field is still very, very challenging. I will just demonstrate that in the context of the data I showed. This is a grassland ecosystem, in China. And what we observe there is this time series, these red dots. And what you are seeing here is, the smoothed curve that sort of follows the red dot. Okay. Now, how do I know this actually follows, an abrupt transition? And as I was discussing with some of the others earlier, one of the features of systems that show discontinuous transition is that if you take the histogram of the time series, it should show bimodality. So the fact that there are two distinct modes means that there are two stable states. Okay, if we have done the same thing here. You can see that y-axis is the estimated density, x-axis is grass cover. So there are so two bumps you can see, one a red bump that actually corresponds to initial time period, and a blue bump that actually corresponds to later time period. Okay, so so this is calculating histograms is also even in the physics literature. Around the critical point is one way you can distinguish a continuous phase transition and a discontinuous phase transition. So here we find that there is evidence for bimodality, suggesting that maybe this is an example of early tipping point or an abrupt transition, but it's not very evident as of now. It does show some evidence for abrupt switch, but we have to understand it better. So another way we do, you can observe this smoothing line, okay, qualitatively. Look at the slope of this, and look at the slope of this, and look at the slope of this. Do you think they're same? So you can actually statistically also show that, if you try to fit as one linear regression across all data points, as against piecewise linear regression. All of you are something what is a linear regression? A straight line through a bunch of data points. A single linear regression versus a collection of piecewise linear regressions. Whenever a collection of piecewise regression does much better than a single linear regression, those are called change points. Statisticians call it change points. That means that there's something changed, there is non-stationarity in the system. Okay. And now if we combine that idea that there's something non-stationarity happening here together with the fact that there's bimodality, that adds evidence to the fact that there was something happened, something like some change, dramatic changes happened here in the system. In fact, it's also visually very clear that the slopes of these are actually, relatively different. And now we can ask the question, now if indeed, and from that change point analysis, what we can conclude is that around year 40 is when the overall dynamics of the system suddenly changed. Okay. Now we can now ask the question, if I had data only up to this year 40, what do early warning signals show? Okay. That's what we'll do in the next, this is the time series of the grass cover. And then this is the autocorrelation function at lag 1, and this is the spectral density ratio. So I want to just emphasize that spectral density ratio is basically the Fourier transform of autocorrelation function. And sometimes just for entirely statistical reasons, spectral density ratio works better than an autocorrelation function. But what you find in both of these metrics is that red line is the change point detected by the time series. You can find that you really don't see a strong increasing trend in either of these two. Okay, so both of these metrics, which follow from the fact that alpha is going to 0, they don't seem to be increasing really as expected as also found in the empirical the lab experiments. Okay, so what we say is that there is no evidence for critical slowing down in this data set. Okay, that's what we conclude. But if you compute standard deviation and skewness, you will actually find that they show very strong signals. So fluctuations show a very strong signal as you are approaching these, tipping year. And meaning, there is evidence for rising variability, but there is no evidence for critical slowing down in this data set. Okay, so how do we interpret this now? So we see evidence for bimodality, we see evidence for a strong change point, right? But there is no critical slowing down. But there is increasing variability. So as I said, 50%. What do I do with this 50% thing? Huh? So this is so he already answered the question. This is an example of noise-induced tipping where you are far away from a tipping point, but stochasticity drove you across the unstable branch. Okay, so how do we explain this lack of critical slowdown with rising variability? So to do this, we have to understand these two types of transitions: critical transitions that happen at the bifurcation point or close enough to the bifurcation point, or stochastic transitions that happen far away from the bifurcation point. And if you now do early warning signals for these two transitions, critical transition, stochastic transition, even in stochastic we do in two different ways. One way is that there is a constant amount of large noise. Okay, that's one way you can have a transition. An alternative way is the strength of the noise is increasing with time. Okay, the driver value is not increasing with time, the strength of the noise is increasing with time. So in this case, there are no early warning signals. A constant large noise case will have no early warning signals. Okay, but this, but the critical transition has all the 4 early warning signals. But this increasing noise driven, that type of a stochastic transition will not have the critical slowing down, the ACF and the spectral density ratio. You don't expect any patterns there, but you expect patterns in variance and skewness. And that's precisely what we find in this data set. Okay, so based on this, what we conclude is that in this data set, what is happening is a stochastic transition driven by an increasing strength of noise. Now you can ask, where is this noise coming from? And so we can say this is most likely scenario for this data set. But you can ask, where is this noise coming from? What we checked was what's happening with the rainfall. What we found was that the fluctuations in rainfall is actually increasing over time in this area. And that could possibly have driven. Of course, it's only a correlational, we don't know whether, and of course, we know that in general, rainfall can influence vegetation massively. Okay. Okay, but it's suggestive that maybe the environmental variability, which itself is increasing over time, could actually cause. And in fact, we know that from many climate models that although even when the mean value of rainfall may not change, variations are expected to increase. And in fact, we are probably seeing already that across the world and also in India, right? We don't see that the monsoon is increasing, but there are periods of massive droughts, areas with massive droughts, but there are also areas with floods. And those events will increase, the extreme events, without changing the average. And in fact, that seems to be true even in this local area. So, the sort of take-home message from this is, when you start to look at real data sets, especially those from the field, you will actually begin to discover things that you don't necessarily include in your model. Okay, and this is an example of that, where we found that in the dryland ecosystem, the grassland recovery was a stochastic transition, and we could infer this based on the fact that there was no critical slowing down, but there was rising variability. Okay, and it was driven by stochastic forces. So, so that's an example of how we can apply these ideas to real data sets. Any questions? And there are lots of nuances moment you get into analyzing real data sets. See, the thing is, in all the models we control every parameter, right? But that's not happening in the data set, in the real system, and therefore the data set reflects all those crazy variations happening in the world. So you have. I don't think so. And that is, yeah, I don't think there will be any. I mean, the thing is, for a given time series, you may still find an early warning signal. That's entirely fluke though, right? Because statistically you don't expect an early warning signal, but some of them may show slight increase. Some of them may also show a slight opposite pattern. But on an average, you should not expect any. But yeah, basically no early warning signals for stochastic transitions driven by a large noise. I think prediction is ruled out. Yeah, I mean, I don't think prediction is possible. Maybe machine learning guys will change it. I mean, as I think Sujit or the other person, Sebastian, was saying, combination of the physics-based methods and maybe machine learning can together do better than what each of them can do on their own, right? So of course, at the end of the day, I discussed this a lot with Narayanan as well. That machine learning will learn features of your data. Okay. Now, when it's learning features of data, it should learn general features of the data, but not very specific features of a very specific data set, right? Then it will never be applicable anywhere else. What are those general features that it will learn? Is it possible that there are some theory that we have missed, some predictions from the theory we have missed? Maybe if there are some general features that we have missed in the physical theories, the theory of dynamical systems, machine learning can learn those general features, I think that would be really remarkable. I think that's where the strength of machine learning can be sort of harnessed. Okay, but not necessarily in learning all the features of a given data set. And it's an ongoing challenging problem. Yeah. And also, I mean, the thing is, at the end of the day, given the time series, right? When we measure early warning signals like variance, autocorrelation, I'm manually deciding a whole lot of things, probably bandwidth, the resolution that I'm sampling data from, and a few other parameters I don't remember anymore. But I guess machine learning can learn all these without probably from the data. One branch of machine learning is the deep learning. Yeah. Can learn these without actually manual interventions, right? But of course, there's always this danger that you will learn too much and therefore won't be applicable for the next model that I'm going to apply to. Okay. Any other questions? I thought I'll just stop here, although I have more slides. I think we should spend more time discussing now than either over coffee or here than more slides. But I thought I'll just show you maybe one thing, which is, because I covered spatial stuff, right? By the way, I'll just show you that, we also did a similar analysis for financial markets. There also, I'll just show you this slide alone, nothing else. So look at the famous 1929 crash of the Dow Jones market. We do not find evidence for autocorrelation increasing in any of the previous financial crashes, by the way. But we find evidence for variance increasing on all of them. Okay. So that shows that critical slowing is not as universal as it has been made out to be by all of us, I guess. So in that paper, what we conclude is that stochasticity is probably unexplained stochasticity is what is probably the driving factor behind financial markets, which is sort of consistent with what finance people would say. If it was anything known, we would have known, right? And basically, rational agents would have adjusted their behavior to prevent the market crash. That's what they argue. Therefore, it has to be stochastic is their argument. I'm not saying they're right. So I thought I'll just show you these pictures to show that the moment you have, when you actually begin to look at actual ecosystems, they're not just some point and something variable over time. You can see that there is, of course, spatial spread of organisms, and the spread of organisms also has many interesting patterns. So this is an example of where, some sort of a, grassy or a bushy ecosystem roughly everywhere, but there are these interesting circles in between of bare patches. And then here's another example of where what we call rabilinthine pattern. They're sort of resembling of some of the coat patterns you see on animal skins. Okay, so you can see that there are again these patches of bare, but there's a connected sort of network of vegetation patterns. And some of these patterns can be explained by the Turing model that Tanveen explained the other day. And this is another patchy landscape. You need to realize that a field ecologist is looking at these landscapes and looking at our theory. And the challenge is to sort of make the connect. Okay, it's not necessarily very easy or obvious. But the fact that there is potentially a lot of data in the spatial spread of how organisms are spread, and understanding those, I think, can sort of circumvent the challenges associated with having long time series data sets. Okay, this is an example of mussel bed. muscles that actually cluster together and form various spatial patterns. Okay, and I think on Monday, Corina Tarnita from Princeton, she will talk about how some of these self-organized patterns suggest suggest metrics of robustness. Okay, so with that I will stop here. So we'll take a break now, and thank you everyone. I'll stop sharing and we can stop the recording as well.